So yes, again, thank you for the opportunity. And what I'm talking about here is a little bit broader view, which I hope is a little bit of a motivation for why we're interested in these optoelectrical or electro-optical frequency combs. So what I should say first is, now you gave me a very nice introduction, so thank you very much for that. I should say that we've been working with this for a couple of years. And I should also say that what you see there on the right is actually a frequency comb in the lab in Aarhus, which I think is pretty funny, because a lot of the stuff that's going on around here is, of course, small chips and very impressive structures. And this is what it looks like when you have a Menlo frequency comb that you have the visible part of. So it is literally our frequency comb. It's not mine, it's the lab in Aarhus, projected on a ruler. It's hard to see on the screen, but it is actually a ruler. And this is the way we're thinking about it. And that might also be a little different than the more communications focus that is very often on frequency comb applications. We are more interested in it from a metrology point of view, which is about measurement science. So what can we do to have this absolute precision on a measurement, for example, on a wavelength, or spectroscopy on molecular transitions and so on. So that is more our focus as a research institution. So let me just, if this thing moved, go to my next slide. There we go. Okay. This is the picture. This is a very simple picture, but it is essentially what we're doing. It's from this very nice Scott Didham's review paper. You take your normal laser light, very pure continuous wave. You send it through one of these lithium niobate electro-optic modulators, and you make your comb. Simple as that. So that is, of course, the main takeaway. In principle, very, very simple. The intricacies is, of course, a little bit bigger than that. So this is what I will introduce today. I'm sure you're all familiar with it, but I will try to motivate why we think this is a valuable field of achieving frequency combs. And it's kind of a different approach than what many other people are doing. So with that, let's just talk a little bit. Very simple. I will introduce who I am. What is a frequency comb? I'm sure you're all familiar with the different types, and then go a little bit more into the meat of the specifics of this, and also our approach to this, and of course, what I'm dreaming of for the future of this direction. So let's go a little bit back. Who are DFM? You have to show this slide when you go around. We are the Metrology Institute of Denmark. That means we are similar to NIST in the way that we have all these standards that are traceable to international agreements. So we are the one who has the meter, we have the kilogram, and so on. We're establishing the time and so on. And this is just a little bit more about how the metrology structure is in Denmark. So when you're standing in California, you realize this are various institutions in Denmark that are spread out with different competences, which is why DFM is a tiny little research institution. We have like 12 people working on quantum technologies compared to big places like NIST. And part of the reason for that is that the competences are spread out. So these other organizations are a lot bigger. So we are the tiny little metrology institute north of Copenhagen. And a little motivation. We work with different things than specifically frequency combs. And that is, of course, also why I'm partly here today, because we are working on several different quantum projects, and we are working on getting more and more into this. And as Zhao nicely pointed out, my background is in quantum optomechanics, so that is also something that I am very interested in still. And that is also why my interest in all of this is. And of course, you can say frequency combs are not very quantum, not exactly a quantum technology, but it could be and will be further down the line. Right? So here I'm showing a couple of the various quantum research projects we're also doing. So the top one there is our reference laser. So that is a fiber-based laser that is locked very, very well to a molecular transition in acetylene. And that is what you use to define the meter. So that is why this specifically wavelength is chosen. You can see the setup over here. It's very simple. You have a good laser, you modulate it to create sidebands. You bounce through a cell full of acetylene. And then you do this saturation-based absorption. So you get a very tiny, very well-defined peak. And this enables you to lock your laser extremely well. And the reason for this is first, that this is the internationally agreed upon way of defining how long a meter is to have a transition such as this, have a wavelength that is so well defined that it can be used for this. And this is one of the ways of doing this. This laser is also interested in optical reference kind of application. So the reason we're interested in it is exactly that we are very good, we claim, at locking lasers. And this particular is a very good way of locking frequency cones. So usually this thing is kind of jittering, moving around. There's this degree of freedom, this degree of freedom. And if you can lock it, say here, perfectly with an optical reference, this is what you do to very well control your optical frequency cone. So I'll get a little bit back on that, but I wanted to show that as an obvious teaser for why we're getting into this. This figure is showing the line width with a frequency cone when you lock it using this one. So that's a measurement done in Aarhus with a Menlo frequency cone. So that means we can show this sub-kilohertz line width at a permanent situation and with an absolute traceable stability. So that means we know what wavelength this is and what it always will be. Very nice for metrology, very nice to be able to use this in spectroscopy. So that's one way the thing we're doing. The next picture there is a pretty picture of an OPO cavity. And this is what is used to make these quantum light sources. And I know several people here have talked about quantum light sources. And this is, of course, the not photonically integrated circuit way of doing it. So we also have activities using that to create squeezed and entangled light. We have several projects with that. And one of the cool ones that I haven't shown here today, but if there's time we can talk more about, is that my colleagues have shown using squeezed light to improve measurement sensitivity. And I think that's a very cool measurement. So they take the light from this one and they do stimulated Raman spectroscopy on a surface. And because you use this amplitude squeezed light, we show a higher sensitivity. So that is something we are very interested in doing, these quantum enhanced measurements. So this is something we are very happy about. Then finally, of course, there's various other things. We are working with characterization of these quantum materials. This is some nanowire project we're trying to use for quantum computing purposes. And we are working with, this is a different setup. This is broad white light, essentially. And then because you know this is very, how to say, it's sort of the same nanowire repeated itself as infinitum. The scattered light introduces the information of the tiny defects. So you can't see a particular one, but you can do very good statistics on the production of nanowires. So this is also something we're working on. So in general, I just wanted to introduce that what I'm talking about here today is what I'm doing with building frequency cones. But what we want to use it for is to combine it with our other interests, of course. So I'm, of course, dreaming of building a quantum frequency cone later. I'm dreaming of using quantum enhanced measurement systems and so on. So let's move on. I will talk a little bit about frequency cones. So if this is way too boring, you have to tell me, because now I'm just giving the broad. So what is a frequency cone? This is, of course, what you all know. This is a little bit too introductory, but we have the whole frequency range here. And of course, visible light is somewhere in the middle as we perceive it. But what's interesting here is, of course, the frequency axis, because there is this difference between do you look in wavelength or do you look in frequencies. So what of course is interesting here is what is the frequency of light? Very, very high. So how do you measure that? You use a grating, you use a dispersive element to measure it, and then you get a color that is of course not as sensitive as what we can achieve with the frequency cone. And that is of course the picture I want to go into, which is that the frequency cone is this ruler. This is again pretty trivial, but I think it is a very good way of thinking about how we want to have this extremely well defined and absolutely constrained permanently. So I can take a single line and I can use it for something. I can have my optical transition in this molecule in my trap, and I can interrogate it with this one wavelength that I know where it is and will always be. This is exactly why we're trying to use this. And of course, with that, the way you do it is that then you take a single cone teeth and you know the absolute frequencies of this. It's 194 point blah, blah, blah terahertz. That means that if I want to measure something here, right? I can all of a sudden measure it on a photodiode and I can count the frequency because I have a cone teeth that's close to it. That is, of course, the dream. So what is it we're trying to build? We're trying to build a pulse train. And the way we do this, let's see. Let's first look in frequency realm. So this is essentially the same thing again. And what I'm showing here is inherently it will dance and it will drift. So we have 2 degrees of freedom. And those 2 degrees of freedom is exactly what I'm showing here. There's this one and there's this one. And so one comes because of the carrier envelope offset frequency, and the other one is literally the frequency cone repetition rate slash tooth spacing. So what this animation is showing is this phase across the various packets. So there's the picture in frequency space, and there's a picture in time space. And one is, of course, connected to the other one. But what you see there is the illustration from Wikipedia showing how the local phase speed is not the same as the group velocity. And this comes back to the axis on the frequency space up there, where you can see the offset is this FCEO. That is how the phase changes from pulse to pulse. So that means that when you have a frequency cone and you want to control it like this, you want to control this phase. Otherwise, your frequency cone is doing this. And what's also worth pointing out here is it's a pulse train. It's maybe trivial, but when you're used to just looking at it like this, it's not obvious that it's a pulse train. And of course, the time here relates directly to the spacing in frequency space. So what we are trying to do in the lab in Copenhagen is to make our pulses as short as possible and as stable and reproducible as possible. And this is how you get as good a cone as possible, of course. So this was the first degree of freedom. The second degree of freedom is this repetition rate. And that is a little bit more a thing you have to work on. So here we see the principle, how you do it, if you can achieve it. So this has been what's been technologically very hard to do, and why frequency cones and photonic integrated circuits have been very hard as well. And also why they got the Nobel Prize for showing the frequency cones like 20 years ago. Because what you need is the span of the frequency cone to be broad enough, as you see here. That's because you need the frequency to be half of the frequency in the other way. You need to take your initial cone and to spread it out. So it takes over a full octave. So the frequency of one end is double the frequency of the other end. This is hard. This is impossible in many systems because showing such a broad cone has been technologically very hard to achieve. And it's very impressive to follow what has happened, because historically, yeah, this is like the holy grail for frequency combs. Once you have the octave spanning, then the next step is how good can you make it, and so on. But if you don't have the octave spanning, you can't reference it with itself. This is what I'm showing here. So what you do in practice is that you make sure you have enough light at one end of the frequency cone, and then you can send it through a nonlinear crystal that doubles the frequency. So you do a second harmonic. And if you have enough power, you get a nice picture out, which is the beat note of these two. That you can see here is actually not one cone teeth. It's how do we just say that? It's like a range you pick out, because in principle, you take one tooth and put on top of the other one, but there's not a lot of power in one tooth. So what the NIST group shows in this paper, and what we will try to do very shortly, is you take several of them and put on top of each other, and then you measure like a collective beat note, which is what they're doing here. So you can see they get a nice beat, but it is like 20 nanometers broad. And when you have this beat, then as the frequency comb does this moves this way, this moves this way, these two change. That means your signal you get out, your beat note, changes. That means you can give feedback on the system. And of course, right now we're just showing generally. So the feedback could be many things depending on your physics, right? If it's a microtoroid, it's a different feedback. It's probably on the laser, but if it's on our system, it would be the RF you put on. I'll get back to that. I'm just saying in general, this means you have a knob you can turn. And this is what is the goal, to achieve a fully locked frequency cone. And when you have that and it's running, then you can really say cone line number 17,203 corresponds to this frequency. And it always does that. And then if this signal looks bad, you can tell it's not. So you know you have this absolute rule for light. And that is, of course, why we care about it. So the picture that is also very good that I wanted to refer to is this. That, as I said before, it is really a way of measuring absolute frequencies of light. That is impossible to do with like dispersive optics. But the frequency cone takes the optical frequencies and transfers them down to microwave frequencies. All of a sudden, you have something in the megahertz, gigahertz range on a piece of electronics that you can measure and have the full information of the phase. Whereas if you put it on a wave meter, you have your laser, you want to see it, you get some precision of point something nanometers. Using this, we can get absolute precision. So that's the picture you should have in mind. What is a frequency cone? It's this way of making optical frequencies practical. Yes. So before I get into the various ways of implementing it, I wanted to show, I think, a very, very cool application for frequency cones. And it also is a little funnier than just me talking. Because what you have here is actually an electro-optical frequency cone that is deployed in a telescope, this Hubble Eppley telescope. And they are using a frequency cone as their reference. And the reason you care about this is because astronomers need absolutely crazy precisions. And the way they do it is they measure collectively. So it's not one cone teeth they use all of them. Because what they care about is the movement of everything, which means you can use the absolute precision of the frequency cone collectively. So I just wanted to show this because this is really a frequency cone of the type I'm talking about today and what we're building that they have deployed in this telescope. And let's talk a little bit more specifics. So now maybe I should have asked for that laser pointer. So what you have over here is the picture of the CCD. So look down here. What you see down there at the bottom, that is the frequency cone. Those dots beneath are the frequency cone signal, and the lines above are the actual absorption measurements for this star. That is, of course, what is interesting for astronomers, because these stars are the molecules in the star. These are the transitions that are visible, because it, of course, it shines out light in all these frequencies, but the molecules that absorb in the what do you call it? Well, the star, I guess, the atmosphere, are shown here. And of course, what you can do if you have very good measurements are measuring these exoplanets. So that's what the figure is showing up beneath. So this is why I wanted to show this, because it's a very practical thing you can achieve with frequency cones. And the picture here is of an exoplanet moving around. We have our observable telescope down here, and we have our star and our exoplanet moving around in a collective motion. And what you see there on the right is then the spectrum moving. And the point here is it's the Doppler effect of the planet moving around. So what you see is you see the star moving because of the motion of the exoplanet, or rather the collective dynamics of those two, of course. You see it in the absorption spectrum. And the point here is this kind of measurement. If you don't have the frequency cone, you cannot get the precision needed to measure these extremely precise movement of these stars. What they can show here is down to like 10 centimeters per second, which is the unit they talk about. And that is the relative motion of the star because of the that you can infer from the motion of the spectrum. And what I'm showing here again is this is only possible because you have the cone here and its ultimate stability. And then you see the motion of the absorption lines above it. So this is just one example of where they have shown this in telescopes. There's several others that use different kinds of frequency cones. But this is just showing the ultimate precision you can get here. And another point is, one thing is it's very precise. Another thing is these people need data for years. You don't just measure for 10 minutes and you get your spectrum and you're happy. It takes days for the planet and star to move around. So you need measurement for years with this stability. So if everything is drifting in this time, you have a hard time. This is why we're excited about frequency cones. So let's very briefly talk about the various implementations. Just wanted to show these. So historically, the frequency cones were built in advanced TISF mode level lasers. And around 2002, or when it is, Theodor Hensch and John Hall, and is it one more, got the Nobel Prize for showing frequency cones. And this is essentially what came out of it. They started the company, or Theodor Hensch started the company Menlo. And what they're doing is that they have this, they call the fiber, what's it called, figure 9 setup. It's essentially an amplifying fiber cavity, to be totally honest. Light goes around the cavity, it gets gain from the erbium doped fiber. So this is a very nice commercial setup that is deployed all over the world, and also the one that I saw in action in Aarhus. And yes, what you get out is your pulse train and your very well-defined frequency cone light. So this is a very nice system, and this is like the, how to say, the one to beat. This is like the famous solution. This is the one that, you know, would be nice to have because it works, and this is a very established company selling these. Of course, they are not cheap. So because of the size of these, the cavity, you get 250 megahertz, and you can tune this a little bit. And this is very good for some applications, and for some other applications, for example, the astronomy one I just showed, 250 megahertz is way too narrow. But of course, for other applications, that could be very good. And this is just a figure showing essentially what I showed before, that they sell components. So you buy a box, put in the blue box over there, and then you get light at visible colors. So what they do is they take the light from the frequency cone, they send it through a photonic crystal nonlinear fiber, an amplifier. And you essentially take all the light you have up in the mid-infrared or in near infrared, and you get it through nonlinear conversion down in this. So that is very nice. Of course, more to the relevance of what we're talking about here is a very, very just a picture to have in your mind, because I'm going onwards to the electro-optical ones. But of course, there's the microresonator curve frequency comes, and this has historically been quite hard to achieve octave spanning width. So of course, you send light in, you have a resonator. Everyone here is an expert in this but me. So this is very cool, but historically it has been very, very hard to get a perfectly fine octave spanning cone width. So I've been following this field for many years, and of course the seminal work of Beha and Kippenberg back in 2007 started a lot of this, where we get really high Q factors in these microresonators. But recently, very impressive stuff has been shown, and very broad spectrum has now been achieved. I think it's obviously a credit to many working on us, but also that now these resonators can be built with so high quality that you can achieve things that you simply couldn't earlier. So this is extremely impressive, of course. And the obvious bonus is, of course, you can make these scalable. It's a completely different approach than these fiber cones, and it opens a whole other world of opportunities. Unfortunately, you have to fight with things that there's material dependencies on the whole octave and so on. It's not trivial, of course, but it is a very, very impressive platform and what people have shown. And it's funny to me also to be here today, because I did spend a year in Australia coupling into these microresonators, like these toroidal microresonators. And it's hard work, but it's also funny because now everything is on a chip. And what I did there was, what's it called? A fiber you pull and you adiabatically make it smaller, tapered fiber, I guess. And just coupling that in was very, very well controlled. But also, once you touch it, you burn it, and you have to start over. So having the whole thing on a chip is, of course, extremely powerful, and the integration. So obviously, I'm not an expert in this. So I wanted to, of course, just tease how impressive this is and the possibilities, especially for communications. And 2 years ago, I would talk about how it's really hard to self-reference and log these, but this has been shown now as well, of course. So I think we should talk more about this afterwards, because you guys are the expert in this. So I will move on to what we are doing, electro-optical frequency cones. I showed this picture in the beginning, and here is a very simple way of writing it up. Essentially, the idea is you add a phase term on your light in a very controllable way. And this phase term is very controllable. It's very much a knob we have on the equipment. And that is one of the pros of this kind of approach, because it is only your electronics that limits you. So we can choose a frequency that's 1 gigahertz or 50 gigahertz. Of course, money starts to become a thing, but in principle, we can choose a frequency we want, and we can change it during the experiment. So that is very interesting for us. So what I've written here is just that it comes out when you add this phase term, that you can write it up in this expansion. What's interesting here is that you get these terms out here, which shows it's a frequency term. So what is more intricate is that it's actually these Bessel functions that it comes out as. And this, in turns, means it's not a trivial shape you get from your mini frequency film. So this is the first step. In our case, you start out with a very good fiber laser that the whole thing is built upon. And then you buy these commercially available electro-optical modulators. So you have one of these, and this adds phase information, and that's essentially just sidebands on your carrier. So that is hardly a frequency cone. I guess it is, but it's a very small one. So what you actually do then is that you combine several of these. And here you see the actual system, a little bit more complicated, but the point is you start out with a CW laser, and then you add more and more sidebands using these phase modulators. And then you can use what I showed before, this non-trivial dependence to carve your frequency cone. And this comes from an interaction between the phase modulators and here the intensity modulator. Because the step we also need afterwards is to make it into this pulse train. Because right now we have just added phase space sidebands. So what we want to do is to make it into this pulse train that I promised, and that will be important in the step afterwards. But what I also wanted to show here, this is a typical of this, what I call the mini comb. This is what you get out, and what limits you is really the efficiency of these electro-optical modulators. So if you had a more strong, what is that parameter called? The V pi is what they specify usually. If one could put a larger phase modulation on the light, of course you would need fewer of them, but this is what people do because these are commercially available. Yes. Yes, that is a very good question. So I have several slides on that, and I think the point is, I wouldn't say one is better than the other, is the point. I think what I'm trying to tell you here today is that this is a different approach, and it gives some benefits and it gives some worse problems. And one is definitely, you can see I need 4 components just to get the start here. Well, I would say mode-lock lasers is a different way, where you really have a TISF that you control well enough, and that's a very hard project by itself, that you make a frequency comb out of that. And then, of course, there's a fiber frequency combs. So, inserting modulation. I think it's a different thing to get out of it, right? So the resonator-based ones are really, these are the only ones that are available, whereas this approach is tunable. So I choose the frequency freely. And there's also a benefit of the stability and so on. So maybe let me get a little bit further. But as I'm saying, I think it's different goals, and I will speed up because I see the time is slipping. So this is just to show this shape here is not trivial. And let's not get into the details here, but if you use different kinds of degrees of freedom, you can turn, here's the phase between the various modulators and the bias and the intensity modulator. What you should imagine is you make sidebands on your continuous wave laser, and then in time, you make a pulse train by carving it out. And depending on which time you carve your laser with, you get different components into your frequency. So I won't spend too much time on this. I just wanted to say that there's also some degrees of freedom that are not available in other types, because we have total control of the signal we generate, and that is one of the main points. So you can say it's not good because it's not stable by itself, but it's good because it's dynamic. So let's move to this one. So this is essentially what we're doing. This is the whole picture. And this is some history. You can see it's fairly new. This is the first octave spanning self-referenced electro-optical comb by the NIST people. And this is their setup. And this is essentially what we are doing. And the difference here is that they use a reference cavity to achieve a very good laser light. We start out with this molecularly stabilized, extremely low line width laser. So this is good for us. The point here is what they show is that you can actually take this mini frequency cone and broaden it in 2 stages to achieve this octave spanning cone. So this is very, very cool, and this is why we're working on this. So sending it through the first step, you get this medium cone, and then you have to fight the noise quite a lot. But then sending it through another step, you can achieve this broadening to an octave. So you have two parts. So you send the dispersive wave one way and the other. So this is the goal, and this is exactly our approach. And as I said, our difference is that we are working with this because we have this idea that we start out with this molecular transition. We will not need to have an atomic clock reference to log it with. We will not need to fight the noise as well as you would if you start out with a normal laser. So that is also what I put here on the advanced. That was my advantages. In principle, everything is tunable. You choose your wavelength, you choose your rep rate, and in principle, you have a lot more power, which is interesting for spectroscopy purposes. It's obviously less interesting if you're not doing stuff where you care about the power in a single tube, but if we are here. Another possibility is that we have a lot more control of the shape of the whole cone, and that, as I said, we can actually control the shape of the whole thing. But what is our problem is that the way you start out, we're taking one and propagating it in frequency, making all these sidebands, means that you add noise. This is obviously exaggerated, but in principle, when you start out with one frequency and you add phasor information, every multiplication of the frequency adds noise. So this is a problem with this kind of stuff, of course. So that is also a problem with other types of frequency combs, but here, this is what we will have to filter it, and we have an optical cavity we are planning to use for, and that's also what the NIST group has done. So we will do better because we start out with a laser, but inherently in these kind of application, you simply add more noise. So let me get to the broadening. So we have this this mini cone, and we want to make it broader. You can only get maybe 100 giga, no, less than. You can get 5 nanometers or something broad cone by itself. You need these broadening steps. So what I show here is various ways of doing it. So this is data where they used it in a photonic crystal fiber. And we are right now using these highly nonlinear fibers. So you see self-phase modulation because your pulses have enough energy to have the chi-free. And you see this nice broadening in the frequency cone. And that is, of course, our dream. And our goal is, or what people do, I should say rather, is to have this full octave spanning cone. So the other approach, which I'm of course very interested in, is to use these waveguides that, well, people like here are experts in, where instead of having this fiber, you make it in a waveguide. And there's all these interesting materials that people have shown. I found these are just 2 examples where the various combs you can see over there. So you send in your pulse train that has this narrow cone. Because of the strong nonlinearity of this silicon nitride waveguide that is designed in the right way with dispersion, you take your light in the center of the wavelength space, and they project out to make this super continuum. And if you do this well enough, you can achieve your full octave spanning cone, of course. But then this is to show that obviously you, depending on who you ask, they will tell you their favorite material is better. So this is just an example I found where they did a similar thing in silicon. And then I found this, which is different nonlinear materials for microcurrent generation. So, of course, choose your poison. Depending on who you ask, I'm sure people here have several opinions about what the best material would be. And to us, it's of course very, very interesting that you could start out with a microcomb somewhere and design your power distribution someplace or the other. Of course, there's a compromise with waveguides because you need enough power and you need it to be nice to work with. But I think it's a lot more powerful. And of course, you can design it in a way that's impossible with nonlinear fibers or even photonic crystal fibers. So yeah, this is showing a couple of those examples. So yeah, just to reiterate what I think our main difference is is that we do not need an atomic, well, we have an atomic reference built in because we start out with our knowledge about these molecular locked lasers. And we start out with a very, very nice laser line that we then put these phase modulations on top of. So our colleagues at NIST did not. So they are locking theirs to a very nice cavity, of course. But not everyone has the facilities that where you can do this. So I think our approach is that we think because we start out with a nicer laser, we will have higher opportunities there. And I think that it makes it very, very interesting. Yes, and of course I can just show here, this is just two ideas. I just wanted to show what we intend to do with it. Obviously, I talked about spectroscopy, that I'm very interested in using our specific comb lines for that. This is the stage we're at now, where we have our not octave spanning, but a couple of, what is it now, 20, 30 nanometers, depending on how much we crank up the power. And what we are waiting to do is to send it through this second step that I talked about. So we have all the equipment for it, but we haven't done it yet. So at this stage, we are at the point where we have a very nice comb and we can use it for spectroscopy. And then I showed this picture before, which I think is a good motivation for why would you do it like this. What I don't think I've said so much about that I would also like to point out is because it's based, these EO combs is based on commercial equipment. It is in principle stable, high power, you can have it running for years, which is of course a thing you would fear about. I know these low frequency combs are kind of finicky and hard to use. So, but I guess everything gets simple over time. So, more recent result I wanted to show. This is from the Kippenberg group this year. And I think this is a funny little thing, and I'm almost done, don't worry. So what they showed here is the combination of an electro-optical comb and a resonator-based frequency comb on chip that they came out with here recently. And what they realized is the need to pump this microresonator with pulses. Whereas traditionally you would pump it with CW, which is what they show up in the top there. And you get your soliton state by itself due to the resonance of the cavity. And what they show in this work is actually starting out with a very simple electro-optical comb like here. This is exactly what we have. You make this pulse train by yourself relatively easy, relatively cheaply. And when you then send that in, you get this resonant, very high energy soliton state in the resonators. So what they showed in this work is, I guess, the power of the EO comb, that it's very, very easy to quickly make some pulses with a lot of energy and insert into their platform here. So I'm sure you've seen this paper, but if not, here you go again. And this one I've already shown. Only 5 minutes late, so we still have a little time for questions. I think I wanted to show this one because I am here. I'm very happy to be here. And this is exactly what I think is a lot of the future in this world. Because what do we need to make better EO combs? We could have a more exotic phase modulation. That is the paper I found of making it in nanomechanics. I'm not sure that's the most realistic choice, but it's certainly a very exotic idea. Probably more realistic is more exotic materials, other ideas, better integration, but probably even more interesting is the combination of cavities with EO modulations on a chip. And this is what they've shown in this work. And I see no reason why everything we're doing could not be integrated on a chip. It is, obviously you need the locking of the laser, but in principle, everything else can be on a chip. So obviously that gives you a lot of possibilities once you have that. So I think that is very, very fascinating, and I would be happy to hear your opinion about what is the focus. The one thing that will be hard to make smaller in our setup is the atomic reference, because the cell of the acetylene is this kind of size. And this is something that's very, very hard to scale down, because many people have tried these smaller rubidium cells, and that works, but it doesn't work as well at all. So this is something that's very much harder than maybe what I'm showing here. But yeah, I just wanted to thank you all for your time, and I hope to speak more to you all. But I wanted to finish up with this quote from John Hall, one of the Nobel laureates from the frequency code. And he has a very nice talk where he gave at the time, and it ended up with this, which I think it's a beautiful little quote. The next decade in optical physics should be a blast. And I think that's even funnier now, because it's quite more than 10 years ago. And he was right. And we continue. So I'll say thank you for your time.